listening to this?
Yes, they
That's
are.
why I hope they're getting some value for their money. So, or maybe not. Anyway, but I'd like to thank the organisers, some of whom are here, for giving us the opportunity to be in such a great space. It's a privilege not only to be in Cambridge, but just to be able to spend time, you know, chat to people, go to seminars, and have a bit of a think without being interrupted. You're all very young, and I'm a bit older, and you come to appreciate these things as you get older and older. So it's great to be here. And these little idle thoughts, I've been maturing in my head, chatting with Andre and Tatiana and Pamela for the last few weeks. And yes, it is a chalk talk. But I have prepared. So, what are the great challenges in biology and physiology? So let's start with a simple question. In a sort of generic, in a generic perspective. Thoughts? I have my own thoughts, but you'll hear them in a minute. But,
How does biochemistry explain your consciousness?
wow. Wow, that's a good one. That's not a bad question. I'm not equipped to deal with that one. That's a very good question.
How does biochemistry explain Donald Trump? Wow, that would be easier.
Yes, I don't think it does. Any other thoughts? So one of my takes on it is, how does structure and organisation affect function? So I think in terms of, you know, I do a lot of work on modelling the heart, but it needn't be that. It can be at the cellular level, the tissue level, and the organ level. So. Seems like a reasonable question, at least. Okay, so second, what are some of the issues in attempting to even address this question? One is issues of multi-scale phenomena in time and space. There's issues of variability. Whatever I mean by that. There's issues of different domains and how you connect the models between domains. What sort of coupling do you have between the models? There's issues in numerics, of course, simulation. Because often when you have multi-scale problems or connected models representing processes in different domains, you have very different timescales. So you might have one timescale in one domain and another one in another. How do you connect them up in some sensible way? So it's things like operator splitting. If your models are non-linear, how do you calibrate them? Not validate, but calibrate. I don't know how to validate. Especially when they're non-linear, for example. So there's a non-linear diffusion tensor. How do you calibrate such a thing from experimental data? Okay, so that's...
Calibrate mean work out parameter values?
Yeah. Yeah. You tell me what validate means.
No, I absolutely agree with you. I never use the word validate.
No, a lot of people
Yes.
You know, I don't like to because I don't know what it.
have to reply to
I don't know what it
referees who
means.
ask me to validate my model, but
Yeah.
I never do it myself.
No, well, I don't know how to, so I
Yeah.
don't bother.
Yeah.
But then we live in a world that we often make simple. So we homogenize or we mix well, shape but not stir, is what the other way around, James Bond. And that, when we do that, that leads us to sort of, we then live in a sort of an exponential world. In some sense. So what do I mean by that? So if you were to try to construct a sort of mathematical framework in this setting, you would talk about the stochastic simulation algorithm, where the waiting times are exponentially distributed. Because you made some assumption about the world that you're describing. It's that sort of world. And then if you were to write down the master equation that describes the evolution of the PDF associated with this stochastic simulation algorithm, you get an exponential function. So you get the probability density function evolves as an exponential.
But it's really that you're combining homogenization with a Markov assumption that's giving you
Yes.
the exponential rate.
Yes, you are. Well, maybe one comes from the other. How does the exponential waiting time, where does that assumption come from? I mean, it's not something that just comes out of the air, right?
I mean, basically, if you're assuming that your state variables are sufficient to describe the state of the system, right, and it's evolution forward, you have Markov property.
Yeah.
That Markov gives you exponential. So what I'm saying is that if you have a homogenized system, but you're allowed to look back
Yeah,
at
okay.
previous states, you could get
Yeah,
that
all right.
exponential.
It's okay. Yeah, that's true. Then we've got the Taulit method, which we all know what that method is, but essentially it's something like you've got this Poisson formulation for the Taulit method. These are the stoichiometric vectors, these are the propensity functions, that's an integral, and you approximate that by the rectangular rule, for example, which would be tau, the time window, times the propensity function evaluated at the beginning of the step, Tn, okay? So that's the Taulit method. Then you have the Langevin equation. The chemical Langevin equation, which is the continuous stochastic representation by approximating the mean and the variance from the master equation. And how do you get that? Well, you can write down the master equation and try and do some things. Or you can work with the Poisson distribution here and say that in some limit, as lambda becomes large, this thing behaves like a Gaussian with mean lambda and variance lambda. Okay, so that means lambda plus root lambda normal 0, 1. So if you then replace this by this, you get the Langevin equation, where my Wiener process is essentially samples from this unit normal distribution. Okay, so the CLE comes incredibly simply from the Taulit method, and hence the Taulit method is sort of an order 1, a weak order 1 method. So all these things connect together in a very simple way, just from essentially having Poisson processes. And then the deterministic limit, the Langevin equation, driven by Wiener noise, converges to your A to B which is just that thing. Okay. And then if I have space, I have the reaction diffusion equation. Well, we all know what that is. So it's a very simple, nice, consistent up and down through these scales, where essentially the exponential world and the Poisson world keeps rearing their heads. So it's a very natural framework. So then the question is, can you do something similar in a setting where you have you live in a heterogeneous world, a spatially heterogeneous world? And so what I would like to do is, well, of course I can have very complex spatial models that capture that heterogeneity in some ways, very difficult to calibrate, but I can have a go at it. Or can I think of an equivalent mathematical formulation that would describe that spatial heterogeneity by some additional parameters, so that you still have a set of models in time rather than just in space.
So when you say, though, so are you thinking of something like the chemical the reaction diffusion master equation? Is that the sort of kind of thing?
Well, we'll see very soon. We'll get to it right now, in fact. Okay, so this is just some background that you all well understand. Many of us have made contributions in all sorts of areas in this space. Maybe the techniques that we use in this space. We use SSA, we use the master equation, we use power leap. These are the simulation techniques. There's binomial. There's higher order methods. That a number of us have focused on higher order methods, where the key idea is to take a Poisson of a Poisson. Oops, I just knocked on that. Poisson of a Poisson, that's the key idea. And if you do it in the right way, you can get weak order too. Okay, there's some details you have to go through. And then there's clever ideas that we use, like multi-level simulation. So this was, most of you probably know this is the work of Mike Giles originally, and it's a form of variance reduction. So Giles, variance reduction. Where you do a sequence of simulations of different step lengths, and you combine across different scales in some sensible way. So what you end up doing is having coarse and increasingly fine representations and a very fine scale representation. And the idea is to do not many simulations at the fine scale, but more as you go up the chain. And if you organise it properly, you can reduce by orders of magnitude the number of simulations you need to do to get certain properties. So this is a wonderful idea. He's got all sorts of awards for these ideas, and we should use it more often in our work. So it's relatively easy to see how you do it in a continuous setting. It's a bit harder to do it in a discrete setting, but you can do it. What else do I want to say? Yeah, so that's sort of about all I want to say. So let's go on to thinking about space. So direction. One of the problems with this space of so-called anomalous diffusion, and people try to claim too much and say it's a panacea for solving all these problems. It isn't, but it certainly can be used. So, molecular crowding. Obstacles, immobile, mobile, binding, unbinding, sliding, diffusion, compartmentalization, different hierarchies. How am I going? Have I missed any yet? Oh yeah, okay. And spatial structures themselves. So I think of the work that I've done in heart modelling with the Oxford group, where you've got fibres and you have sheets. How do you represent those spatial structures in ways that you can actually calibrate models against data? So you've got all these sorts of aspects. And then what might you be able to do? Well, we've got people in this very room who've thought about that problem, for example. So you can, sorry, no, I missed that one. Sorry, 1 minute. Back to the start. Where you can write down a modified reaction diffusion, in which the diffusion tensor is no longer constant, but it's has some nonlinear property. So you can modify the reaction diffusion equation. So John Chapman, Maria, I think Ramon is also considered these things. Then there's people have thought about, well, let's go to this one, obstacles, immobile and unmobile. So if the obstacles are moving, you can actually write down a spatial master equation. You just think of them as a chemical species, and you can write some things down, and you can do some nice analysis. It becomes harder if they're not moving, in fact, and you can't really use that approach. So you can modify the master equation. Binding and unbinding. There was a very, very interesting talk last week. I've forgotten his name already. John. Yes, that's right. Who was precisely talking about this problem. And the distributions there had a certain characteristic shape that were very characteristic of the probability density functions associated with anomalous diffusion. And this is one area where anomalous diffusion does make sense. Perhaps it makes less sense, certainly, up here. And so on and so forth. So how do we go about developing models that can be well calibrated, that can describe diffusive and chemical processes in these structures? All right, so every time you have a different modelling environment, you can try and build a different type of model, maybe biophysically functional, or it might be just phenomenological. Or we can say, well, what are some of the key ingredients of things that can happen in this space? One of them is, at least here and here and here, it's not quite so clear, perhaps here, is resort to this concept of anomalous diffusion in time and or in space. And anomalous diffusion is characterized by a process which has a heavy-tailed distribution. So we're no longer in an exponential world, we're in another world. Okay, so let's try and move to that world. If there's anything you don't like or you want me to try and justify, then just ask me. Okay, so I think that's maybe the only other thing I want to do. So in this spatial world, where we're trying to simulate diffusion and chemistry in these increasingly complicated spatial structures, the sorts of things you can use are Smolden, Stochastic, although that isn't really in space, it's just a bunch of routines from Linda Petzold's lab. Linda Petzold and Per Lostedt, amongst others. You might want to use approximate Bayesian computation via sequential Monte Carlo. Another clever variant is something called Hamiltonian sequential Monte Carlo, which has a sort of momentum turn, which seems to be quite effective. So these are ways, of course, of just calibration, parameter fitting. You can build populations of models, ensembles of models. To capture the between subject variability and then do probabilistic predictions. Okay, so these are all techniques that one might use to tackle the simulation aspects associated with modelling in these spatial structures. Okay, so but let's live in a different world for a moment. So let's live in a heterogeneous world. But it's a world in which I just want to develop temporal models rather than detailed spatial models. So I want to capture some key aspects of the heterogeneity in some way. So the models initially are temporal in nature. They're not spatial, but they try to capture spatial characteristics. Of course, they can be spatial. And let's identify two scenarios. One is crowding. And I'll explain formally what these things are. So let's just write down anomalous diffusion. And one of its characteristics of anomalous diffusion is that the mean squared behaviour is sublinear. So it behaves like t to the alpha, where alpha is less than 1. So this is anomalous diffusion. So associated with this are heavy tail distributions. And so the sorts of, if you were to write down a diffusion equation in this setting, what you would see something that looked a bit peaky and spread out, whereas in the standard setting, you would see probably, well, you would see some sort of Gaussian. So it's not quite that peaky, but it has that sort of characteristic diffusive shape.
Is the first thing, I mean, second the consequence of the first? Do you have to have heavy tails just because the means?
No,
squared?
no, you don't. No, it's just one characteristic of this stochastic process. The stochastic process associated with anomalous diffusion also has it doesn't have exponential waiting times. It has waiting times which come from the so-called generalization of the exponential function called a Mittag-Leffler function. So the waiting times come from this Mittag-Leffler function. Let me write it down.
Waiting time for what?
Sorry?
Waiting time for what?
Okay. I'll come to that in a minute. I've gone ahead of myself, as I sometimes do. So it has a function, it has an infinite expansion, j to 0 to infinity, z to the j, gamma function, 1 plus alpha j. So that's the Mittag-Leffler function. Alpha here is a number between 0 and 1. When alpha is 1, this is the exponential function. When alpha is between 0 and 1, you get these heavy tails that look like this as opposed to the exponential function looking like that. Okay, so this is again a characterizer associated with anomalous diffusion. And then the other type of effect, and I'll characterize this mathematically in a minute, is superdiffusion, sometimes called ballistic motion. And it's associated with a levy process, which is just a jump process. But it has the one characteristic, that its mean squared behaviour is t to the alpha, but the alpha is bigger than 1.
Isn't that where you get the heavy tails and the marginals?
You also get those, yes, you do.
But you don't get them in the first necessarily.
Yes, you do. All right.
In the position.
Yeah. Yeah, I'll say a bit more. It's because if you were to write down a diffusion equation in this anomalous setting, then you would find that if you did an eigenfunction expansion, the eigenfunction expansion would be in terms of Mittag-Leffler functions rather than exponential functions.
The fractional Brownian motion would satisfy the anomalous diffusion.
It would also
It would have a Gaussian margin.
Yes. So this is not fractional Brownian motion. Yeah, you're right.
Maybe if you have a is it because you have a Markovian process and you're violating the simple limit theorem even by subdiffusion?
So here you don't have a Markovian process.
That's something different.
You don't have the Markovian process. Okay, Brownian motion use, you can also use that as a model. So it's modeling something a little bit different. So it's not this. So certainly, when I talk about these things, and I have physicists, they can certainly get their heads around this. But this one, okay, what does this ballistic diffusion mean, this superdiffusion? Because you get these, you can get arbitrarily long jumps, and if an object has mass, then that's sort of hard to happen. So sometimes you see papers written on the behaviour of albatrosses, and they talk about the albatrosses. The underlying process is a levy process. Well, it isn't really. It's a levy walk. So there's a difference between a levy process and a levy walk. And a levy walk has a finite velocity, so you can only move so far. However, my take on superdiffusion is that, and I suppose we've used it in our HART modelling, is that the spatial structure it consists of many interlocking spatial scales that are not well separated, and that they form connected pathways in the tissue. So depending on the path that the ions take, they can move large distances along connected pathways or not. So there's a wide variety of spatial scales that come about from the interconnected pathways available in the tissue. The other way to think about it is in terms of electric fields, that I won't go into. So that although I agree that there's some dubiousness about using Levy processes, nevertheless, it's not completely dubious. So there are some settings where I think it makes sense. Okay, so let's try and formalise this a bit more. So the model, one of the models I have in mind is I have diffusion on a lattice, and so the particle is diffusing on a lattice, and at each point there's a waiting time. Okay, so the size of the circle is related to the waiting time that this particle, this pen spends on the lattice. And so here at the moment, in this setting, the particle is still moving the same increment each time. So that's not a jump process, but there's a waiting time distribution associated with the size of these circles.
But it's not continuous space, I wouldn't call it a diffusion.
Well, it's a random walk in an element. It's a diffusive process, which I will write down.
Okay.
Yeah, it's a random walk.
It's not
It's a random walk.
But is a diffusion process?
I'm going to take a limit in a minute.
Has a diffusion process only when you assume that the waiting times are exponentially distributed, or is it always
No.
a diffusion process?
No, well, it's a different type of diffusive process. We'll come to it in a minute.
Okay.
We'll come to it. But you have to take the limits. So the diffusion parameter is no longer, delta x squared over t, and you take the right limits as delta x and t go to infinity. You have to take a different sort of limit. So, supposing we had a PDF of phi, x and t, that described the distribution of jumps and the waiting times. Okay, so let's lambda of x, let's integrate over, I'm integrating over time, phi of t, and let's have the waiting time, which would be integral. Okay, so let those be the waiting time and jump distributions. And then you could define, say,
Are you really integrating?
sorry?
Do you really mean to integrate in X? I thought we were on a discrete lattice.
So these are distributions. So they're not.
Are we still on the lattice?
No, they're not on the lattice now. No. They're the underlying distributions, and not on the lattice well. No, not on the lattice well. So the characteristic waiting time would be well, put S here, S here.
You mean infinity?
Yes, I do mean infinity. And I probably meant infinity there as well. And the spatial distributions have characteristic would be, what would this be? Where am I? Squared x dx. So, what should I call this? I don't call it big T. So if big T and that are finite, and essentially we're in a Brownian motion world. Okay? If T diverges, but this is finite, then we're in an anomalous diffusive world. Described by a certain type of stochastic process. I'll write down in a minute. And then if T is finite, but this is infinite, then we're in a super diffusive world.
Curious, why don't you, I mean, I would have called the first thing subdiffusive, and I would have thought.
Yeah, well, you're right. I see. Let's do that. It's used. Yeah, that's a better word. Let's call it subdiffusive. Okay, so these things broadly characterize the types of behaviour. Well, let's. Okay, so that was. So section 8. So we can write down. All right. So then, if we go to our lattice and take an appropriate limit, we can write down a diffusion equation. So in the subdiffusive case, so I think we're into section 8. So in the subdiffusive case, you end up with a model that looks like this. It's an alpha. So, alpha is our number between 0 and 1. This is the standard, I'm in 2D. Well, this is standard Laplacian. This is the diffusion constant. But the first thing to note, it has different units to the standard case. It's got to have fractional time units in there. So, we grab the units. And then in the super diffusive case, delta t. So it's a standard time derivative because yeah, t is finite. This t, w of x, is minus so you get this. So it's right. So it's fractional in time, standard in space, standard diffusion in space, standard operator in time, but a fractional Laplacian operator in space. So this is just the fractional Laplacian. It's got the same eigenfunction expansion as the Laplacian, but its eigenmodes are eigenvalues raised to the power alpha upon 2. Okay, so this, and that's why these things are called non-local problems.
If I have to take A equals 1 here, should I just go back to the diffusion equation?
Alpha equals 2 should be the, so that's the Laplacian.
Okay.
Okay, alpha equals 2 is the standard case. So the reason is, the reason it's called non-local, if you approximate the Laplacian by a standard finite difference approximation, so then you have some tridiagonal matrix, for example, or it's block tridiagonal, and you raise it to the power alpha, where alpha is not 2, then you get a dense matrix. And so that's why it's called non-local. So that means that things that are happening here are affected by all the other points in space. The effect may be quite small out near the boundaries, but that's why it's a non-local problem.
Well, we can see more directly that if you just did the inverse Fourier transform, you would get some sort of scaling kernel, right? That would
Yes.
not be like a
Yes,
delta constant.
exactly. That's yes.
I like his explanation better.
But you're right. You're right. And of course, if you have some chemistry, you can put some chemistry. So now we need to know what do we mean by this object. So that's called a Riemann-Liouville fractional derivative. There's also another representation which is called the Caputo derivative. So in time dimension, just in time, the Caputo derivative, I'll put a C here, and it depends on where you start from, so I'm always going to start at 0. And my initial point would always be 0. And I'll put a little t there, that's a function of time. So it's the integral of y with t. It's the integral from 0 to t. 1 over gamma, 1 minus alpha. And this would be y prime of s ds over some kernel which is t minus s to the power alpha. Okay. So it's a integral with respect to a kernel with some appropriate scaling value here. So this is called a Caputo derivative. If it's a Riemann-Liouville derivative, there's some difference because you take this derivative outside, so they're not equivalent, but there's some little thing you have to do at the initial value just to equate them. So that's called a Caputo derivative. And so
If you did a Laplace transform in time, would you just multiply by some power of the Laplace variable?
if you did a Laplace transform in time, you essentially get things that look like Mittag-Leffler functions.
So it's not so simple.
So that's where they come from. So there's no exponential anymore. So we're not in an exponential world, we're in a Mittag-Leffler world. A world where there are heavy tails. Okay, so, and such a problem has memory. And the memory always goes back to the origin. Okay? Because of this kernel. Probably I'm getting a bit technical, is it okay? So, of course, what you want numerical methods for solving these things. So you would like a finite difference approximation. To the Caputo derivative. Okay, so a finite so there's something called the Grunwald-Letnikov finite difference approximation. And because it's now non-local, it will have influence from all values of y back to the origin, back to where you started from. So d alpha, Caputo derivative y at Tn will be, you can approximate it as an order 1 approximation, 1 upon h to the alpha, sum k equals 0 to n, minus 1 ck alpha ck y.
How do you define the initial value or boundary values for these kind of equations?
Yeah, so for a Caputo derivative, okay, so for the Caputo derivative, there's not really an issue, but for the Riemann-Liouville, there is an issue, because in a Caputo derivative, the derivative of 1 is 0. And in a Riemann-Liouville approximation, the derivative of 1 is not 0. In fact, it's t to the minus alpha or something or other. Okay, so you're exactly right. There's an issue with what happens at the origin. But if you use a Caputo formulation, that sort of goes away to some extent. Okay, there are issues with boundary conditions in a PDE setting. That's a different problem. So you have a numerical scheme here. Right, so if I wanted to solve this problem, I discretize my Caputo derivative by this finite difference approximation. I discretize in space. And now I've got this at each point. I've got yn in terms of yn minus 1, yn still all the way back to y0. And when I go to yn plus 1, there will be influence from yn all the way back to y0. So the influence just keeps on growing and growing and growing, but the influence also, the size of the influence diminishes the further forward in time you go. So at some point you can window it and cut it off. And so that's where all this memory comes from. So.
Yeah, so I mean, is this related to the 18 that Metzger was talking about last week?
Probably I was in Edinburgh, but I could believe it.
There was sort of this concept that you had this, yeah, so you had this like essentially permanent memory of the initial conditions. I guess it was just slowly decaying.
Yes.
That's the same thing here.
Yes.
Slowly decaying.
Yes. Exactly. So it's slowly decaying because of these are just the combinatorial coefficients, except alpha is no longer. If alpha is 1, then you only get an influence of k equals 0 and k equals 1. This is just the backward difference scheme. Okay, alpha is not 1, then there's influence. Okay, so I'm sort of getting to where I want to be. You might say, well, I haven't spent my 5 weeks very well because. On the other hand, these things aren't so trivial. So, let me go now to, so what I want to do in maybe 10 minutes is say a bit more about numerics and then a bit more about what a Taulich method would look like in this space and what a Langevin equation would look like in this space. Because I want to construct this sort of mathematical framework. So I apologise if this is not so much biology, but there is ultimately biology and physiology in here, I can assure you. The alpha y is 0 equals something. So the fundamental equation here is, in a linear setting, is d alpha y equals ay. Now, if alpha is 1, we know the solution is the exponential of at. If alpha is not 1, the solution is this Mittag-Leffler function. Now, it turns out that when we come to writing down master equations associated with these anomalous diffusive processes, you get things that start to look like this.
Sorry, I'm confused because I thought you were saying that because this thing has this non-local memory, it's not just going to depend on what y was at t equals 0. Are you making some assumption about what? Oh, are you assuming y is 0 before t equals 0?
No. Y is. It's everything is defined from an initial point because it's in a Caputo setting. So I have my initial value. I compute y1. So if I was to write, okay.
Sorry, yeah.
No, that's a good question. So if I was to write down this finite difference scheme for this problem and take the limit and expand it, I get that. So it's just the generalization of the exponential of the matrix to this non-exponential world. However,
So your initial value is just one point.
yes,
Every
exactly.
number in this case.
Yes, exactly.
Okay.
Yeah, no, there's no issues whatsoever. Yes,
So to get from y0 to y1, you only use y0.
yes,
To
exactly.
get from y1 to y2, you use y0 and y1.
Exactly.
And so on.
Exactly. It's exactly that.
This is strange.
You don't need.
But it's a rule.
You don't need that information.
But I guess in some
It's
sense,
not like
It's not a delay where you need paths.
Exactly.
It just came into being.
That's a big bang.
Yeah.
However, the nice thing, I can do an integral representation of this. So I can integrate this both sides. But my integral operator is a fractional integral operator. So if I was to do that, I can write the solution of this down as y of t equals y0 plus this integral term. This fractional integral is in some sense the representation of this in an integral world and a differential world. So this I alpha of f of y of SDS is the integral from 0 to t with respect to a kernel. The kernel is the same thing here except the power is different. So it's t minus s to the alpha minus 1 over gamma alpha f of y of s ds. Okay, so the solution of that is this thing, where this fractional integral is defined with respect to this kernel, raised to the power alpha minus 1. So then you can apply a quadrature formula to that, and you will have a different finite difference representation, but which would be equivalent if you applied it in a derivative setting.
Is f of y that expansion there?
No, f of y is precisely just this thing.
And what is it?
It's just a function. It's the right hand side of the derivative problem.
I mean, it used to be that,
So it's-
spatial operator, right?
So now forget about space for a moment. Just go to, here's an ordinary
Well, you
differential
mean like-
equation in time.
okay.
You give me your favourite function of y, which is nonlinear. I compute the solution of that fractional differential equation. Okay? But I can write it in this integral form. And that's sort of cool.
And f of y of s is just some other function of s.
So you move to the non-spatial sort of version first and then go back to the
Yes.
spatial.
Yes. Well, because what I'm claiming now is this parameter alpha is one way of characterizing some spatial effects in a heterogeneous setting. Right, so I can put a quadrature formula on this. I have a numerical method. Okay. So to finish off and to show you that I've actually not wasted 5 weeks of my time and everyone else's time, I would like to think about, and there's other things I've done, I'm going to run out of time, but I want to think about what a Tau-leak method would look like in this setting. So I've jumped over lots of stuff just because I haven't got time. So just think about that problem. X is decaying with the rate lambda. And if we were to write down the Poisson Tau-leak method for this, what would we get? Where tau n is the time between Tn and Tn plus 1. Okay? Maybe we'll put a tau in there if you like. So that would be the Tau-leak method for that problem. No, it wouldn't.
So what
Sorry,
is
no.
Is x either 0 or 1?
Xn, sorry. It's just my brain is starting to go, that's all. Okay, so lambda xn tau n. Let's make tau constant. Let's make life simple. Okay. So that would be the Poisson Tau-leak. Agree?
This is a death process.
It's just this process. It's just this process.
X subscript n is the number of x
Yes.
molecules of
Yes.
states. Okay.
Exactly.
Right.
And if you were to take a conditional expectation on that, we know what the mean of a Poisson process is. So we take a conditional expectation, we write down the mean. We would get that. We take a conditional expectation using the fact that the expectation of the Poisson process with parameter lambda is lambda. But you have to take a conditioned expectation. That's just the explicit order method. So all that tells me is that there is a relationship between the Euler method, the explicit order method, and the tau leap, which we all knew in any case. Okay? But now, I would like to write down a tau leap in this setting. And so, what I'm going to write down is, so what would I write down? The key is this, thinking about this thing. So what I'm going to write down.
Hang on, what's the equivalent of the first line first? So you've got x with rate lambda goes to 0.
Yeah.
Death process with rate lambda.
Yeah.
So now you're talking about some different process.
So yeah, now I'm talking about a different process in my subdiffusive setting, based on, well, what needs to happen is that in some appropriate limit, the solution to the tau leap, here or here, converges to the solution of this fractional differential equation. So what should happen is I have to write down a tau leap method such that when I take an appropriate limit of it, it will converge to the solution of.
So what I'd like is, so I can say that death process says that every member of the population in the time interval delta t has probability lambda delta t of dying.
Okay.
Yeah, independently. So what do you say?
Yes, that's a good question. I haven't figured that bit out yet.
Because
it's not so simple. Because this is no longer Markovian.
Right.
But there should be a stochastic
No,
description.
there should be, and that's why I need another 5 weeks to get no, you can't have everything in 5 weeks, right? So give me a break.
So somehow you know what the maths is, but you don't know what the.
I know. So I'm working. I know what the solution and the limit should be in a deterministic setting. I know what the Langevin equation should be. I know what the Poisson tau leap should be. It's hard to write down what, say, the SSA would be because of the memory term and the fact it's non-Markovian and you don't have stationary increments. It's not entirely trivial. I've tried different things, but I still haven't quite nailed that. So when I've nailed that, then I'll have nailed the whole multi-scale thing.
Let's see if we can get one thing. There's 5 members of the population. Is their deaths independent when you have this anomalous model?
So let me write it down, and you'll see what the. So what I want is in some appropriate limit that this thing in mean, when I take the mean, will converge to the solution of this thing, which is a Mittag-Leffler function. So that's what you get with the standard tau leap. And so let me do that. So let's write xn. So it always has to go back to x0, because there's always an influence back from the initial starting point, because of the memory term, minus Poisson. And now all I've got to do is take the Poisson of this integral operator. So I'm just going to write down the Poisson of the integral from where? From 0 to Tn of lambda x of s ds. So I have this thing here. So what you see is that, okay, what do I mean? Then I discretize this thing. So I discretize this integral, and this integral becomes some linear combination from j equals 0 to n of weight functions, maybe n minus j. Oh, let's do this n minus j xj. And these weight functions are the weight functions you get when you discretize this integral in some appropriate fashion. Okay, so what this, and you can see, so if you were to take, this is still Poisson, but it has a Poisson of all this past history. And you were to see if you take the expectation in a certain way, the fact that this thing looks like this thing, which will look like the solution of that in the linear case, this will converge to this thing. Will converge to the Mittag-Leffler function. So I claim that this is a Poisson-Tau leap. It's an order 1 convergence to the, in the mean, right, not in anything else, to the corresponding fractional differential equation, which represented by a decay problem. Okay, so that's where I'm up to. So that's where the memory always goes back to. So it involves x0, x1, x2, all the way up to xn. So you start off x1 equals x0 minus Poisson lambda x0 times tau. So the first step is just a standard tau leap. But the second step is x2 equals x0 minus Poisson x0 plus x1 with some weighting. x3 is Poisson is x0 minus Poisson weighting x0, x1, x2, and so on. So this memory sits there, it doesn't go away. It can diminish as you go forward in time, but it still sits there and annoys you.
Did you say x3 is x0 minus some?
Yeah, so you always go back to
it's
the...
not x2 minus some.
No, it's not. I could write it in terms of xn equals xn minus 1 in some other, with some other thing over here.
It doesn't make any
Doesn't make any difference. It's still a it's not a Markovian process, and it has problem with the increment.
But, I mean, here's my concern with the approach, which is essentially your y of t equation is an evolution of the single time marginal of whatever stochastic process is underlying this whole thing. And you're verifying that your numerical method is going to construct the single time marginal distribution, or converge the single time marginals of your numerical method will converge to the single time marginal distribution that it should. But don't you also have to check? I mean, that's why I guess I'm concerned about what's the underlying, idealized stochastic process. Do you have the correlation structure correct with this method?
I think I do. I need to. So I think I absolutely agree. That's important. I completely agree. I think I do have it with that method. What I don't have, perversely enough, is a clear understanding of what the stochastic simulation algorithm looks like in this setting, because it's non-Markovian and there's problems with non-stationary increments.
But it seems like, I mean, I'm just making up a possible stochastic model. That's not us to say, but at least it's a stochastic representation. Is to say, if I have a population of X individuals at time 0,
yeah,
each of them independently has some hazard rate as a function of time to die.
Yeah.
Right? And then that kind of memory, if the hazard function is not constant, and then maybe the marginal of that is, this thing, right? If you give it the right kernel.
So maybe. So I mean, I'm gone over time. I apologise, but let me sort of finish this off. So yeah, I mean, these are all good questions. So one obvious thing to do. So there's something, for example, called fractional Poisson equations. So fractional Poisson equations are examples of a time change stochastic process. So if I have a process x of y of t, and if I make, so you can see where I'm coming from, if I make x Poisson, and if I make yt, yt has to be non-decreasing, has to be independent of y, has to have some other properties as well. So this is called a time change process. You end up with something called if you make this sum appropriate, it's called an alpha stable symmetric process. Then you end up with a fractional Poisson process. And then you might think, well, okay, that's the object I want, because it generalizes, you generalize Poisson processes to the fractional Poisson process with this exponent alpha. So cool. And fractional Poisson processes have Mittag-Leffler weighting time distributions. So again, it makes sense. So what you could do, and we tried it, is to just do the SSA. Xt at tau equals xt plus nu j where the waiting time is selected from Mittag-Leffler waiting times. But, you know, where's the memory in there? So it's still Markovian in some sense, because xt at tau you just get from x of t, even though the waiting time is a waiting time associated with a fractional Poisson process. And in any case, if you do that, and then you compare it with the deterministic in the limit, you don't get the right distribution. So that's not the answer. So something obvious. So that's why otherwise it would, you know, I'd have made a little bit more progress with the SSA.
Would it be helpful as well to think if you are saying that you want to use this subdiffusion to describe, to incorporate inhomogeneities in space, but without having space explicitly? Would it be something that in the SSA you actually need to have special inhomogeneity somehow through interactions between the different?
I think there is some stochastic process in here of which this is some higher level representation. I just haven't figured out what it is, and it's not the obvious things that you would write down. So I agree, it would be wonderful if I knew how to do that. Do two good questions from here, but at the moment I don't. But I'm fairly convinced that this is the right sort of representational form in the Poisson setting. Okay, so where do you go with this? Then the idea is you can construct a hierarchies of models that mimic in some ways a simulation in constrained spatial structures. You can't overstate it too much because there are many different types of spatial structures, and you know, one spatial constrainment is very different to another type. But nevertheless, I believe that developing a sort of multi-scale theory in this setting can lead to different ways of doing temporal simulations, and in these spatial simulations as well, taking into account some heterogeneous structures in space. What's hard is, people ask me with the heart modelling, well, if you're going to have a fractional diffusion equation, what's my alpha for my heart? This isn't a good. Or here's a slice of histology. Yeah, tell me the alpha, please. So I say it's a silly question. Go away, because I don't think it's the right question. But it's not quite. I'm being a bit flippant. It is an important question because if this has to have some meaning beyond just a bunch of interesting stuff in mathematics, then there needs to be some understanding as to what sort of spatial structures lead to these sorts of things. Otherwise, it may not be biophysical in nature. It could still be phenomenological in nature, and you can still fit parameters to it against data, and probably, you know, get good insights. But it wouldn't necessarily have a biophysical meaning. So there is that disconnect that needs to be filled. Anyway, so thanks for listening. I tried to do it as best I could with my failing memory. Lots of good questions. If I knew the answers to some of them, I'd have told you what the answers were. Anyway, thank you.
So finally, having this alpha is like, you started with the idea of going into some kind of heterogeneity. But here, by having some kind of uniform alpha, we gain some kind of rehomogenization in something that is like uniform, like yes. for the entire process. Yeah,
so I like to think of it as, it's a sort of homogenization in some strange way that I don't know enough about homogenization theory, but it sort of is. But the nice thing is, supposing you want to connect up processes in two different domains which have very different properties, then you know, you can have an alpha and a beta in some way, and so you connect it up. So it gives you some power in being able to connect processes occurring in different spatial structures that you wouldn't normally have through some sort of homogenization. And this alpha doesn't have to be constant; it can be time dependent. Could be space dependent even.
So if you have here an alpha that is, let's say, time dependent, everything will work.
See
I mean, I haven't followed.
No, but what you see in these models is you see this sublinear, mean square behaviour. But we know that in some cases that, initially, so there are short-term and long-scale diffusion properties, and things can start off linear and then they become sublinear. So anomalous diffusion doesn't capture the linear bit at the beginning, but you can have a 2-scale process and do a much better job, for example.
And, in terms of the spatial structure, if that f of y, if we replace it by Laplacian, then we come back to the initial
Yes.
equation. Is that sort of a relatively straightforward thing to do in terms of what you described here?
Yeah, yes it is. Yes it is. Yes.
You just couple the special point who's neighboring to it.
Well, you have to be a bit careful in that setting. So it depends on whether it's time fractional or space fractional. So the summary is time fractional, these things, have memory all the way back to the initial starting point. Okay? Space fractional have non-locality in space. So every point in space influences every other point in some way. And there the boundary conditions are a bit subtle, in actual fact. You have to be quite careful.
Or you can do the case gamma and t both go to infinity, where you'd have a non-local in space and time, right?
Yes, even more things to do, indeed.